Okay, so finally, let's look at the canonical viewing volume. So we went all the way from the setting up the viewing volume, looking at the commands. We looked at the perspective projection, which resulted from the frustum, and then we looked at the orthographic projection, taking that rectangular area into the canonical viewing volume. But what we haven't talked about is the canonical viewing volume. So here it is. We have this cube sitting at the origin with a side length of 2. And this is the volume which the rasterizer deals with, right? So when we do our matrices, our matrix operations, our multiplications, that happens before the rasterizer. We are in homogeneous coordinates still. We haven't done any homogenization. So the division by the homogeneous coordinate is not yet happened. And we're going to go into the rasterizer, and then the rasterizer will take care of the rest. Square at the origin with a side length of 2. When you look at the OpenGL matrices, actually the image plane will end up at z equals -1. Here I didn't show it like this. I showed it like the way we derived the matrices, so with z equals 1 as the image plane, but this doesn't really make a big difference. Once we have this scene, or our scene in the canonical viewing volume, all properly scaled and translated and perspective projection applied, then we can look at how do we get from this canonical viewing volume onto the screen. So how do we get to actual pixel coordinates, right? Because our screen obviously has many pixels and doesn't have a side length of 2. So we have to do another final step to get to a buffer or to screen coordinates. For this, we have to mainly look at x and y, and then I will say a little bit about z as well, but let's just look at x and y. Then our left side is x minus 1, our right side is x equals 1. Our bottom of our cube is y equals -1, and the top is y equals 1. Now, when we look at the screen, as I said, we have pixels. So we have a pixel in the very upper left corner, which is our pixel 0, right? Our 0, 0 pixel, so to speak. And we have then a certain width and height for that window. Maybe, maybe it's 1080p, or maybe it's 640 by 480, or whatever the size is. So this window size here, this is clearly that the coordinates are not from -1 to +1. So how do we scale in between? And how do we set that scaling up? So I say up there that we can use GL viewport to determine the size and width and height of that viewport. So the width and height is nx and ny here in my example. And then you probably wonder, why is he applying this -0.5 here? This is simple because we want to have the upper pixel to be 0, 0. But I want to have the center of that pixel correspond to the actual coordinate. So if the center of the pixel is 0, 0, then if I go to the corner of the pixel, I have to move half a pixel over to reach the corner. So I'm moving half an over in x and half over in y. So that's why I'm getting x equals -0.5 and y equals -0.5 to be the upper and the left side of my actual screen. And because I'm subtracting half over on the left, of course, I also have to have half on the right and on the bottom. So that's where this comes from. Now, what operations do we need to do to get from this 2 by 2 to pixels? We can use our favorite way of looking at this. So this mapping to go from the canonical viewing volume to screen coordinates is nothing else than another matrix operation. Here as an object transform, right? Object transform starts always a little bit awkward. We have to put everything together at the same coordinate system. Then it looks like this. Notice that I flipped them around. In this case, the canonical viewing volume is upside down, just so that the coordinate systems align, because my screen coordinate is, of course, a left-handed coordinate system, and the y-axis is going down instead of up. So that's what I start out with, and then I can change things around. For example, I can flip one around. So I'm doing a reflection, so a scaling in y by -1. And then I have both essentially upside down, so to speak, or rather I have now in both aligned in this way. Then I have to make sure that they have the same size, so I'm going to scale it up, the canonical viewing volume. Well, I zoom up because probably we have many more pixels. So I scale to screen coordinates here, so that's a scaling by width half and height half. And again, it's half because we're starting out with a side length of 2. And then we move this over, so I have to move it down, translate it, so that we end up with the canonical viewing volume aligned with my screen here. So I need this translate. So I need to do scale the reflection, then scale to screen coordinates, and then translate to the right position. So if I write this down, here I have my reflection in y, then I have my scaling. I'm dropping here the z-axis, just doing it in 2D. We have this upscaling to nx half and ny half, and then we translate down to the right spot. And again, there's the half in here to take care of my half pixel. So overall, this is my mapping from canonical viewing volume into pixel coordinates. And this minus sign comes from the reflection. Now I can also talk about this as frame transform in reverse. That's probably more convenient. So I'm starting from in the upper right corner from the final situation, right? So, and then I think about what I need to do. I need to move my coordinate system, in this case, down to the center. And then from the center, I can scale it up. So here I'm scaling it, and then it's big enough, and then I flip it around, and I get to the start position. And because I'm thinking of this as frame transform in reverse, it should be the same result than what I have done before, thinking of it as objects. So when I think of it as a frame transform in reverse, then of course the matrices, they need to be multiplied in the proper order here. So I'm going from translate scale to reflection. And because it's a frame transform, I have to multiply them together from left to right, right? So I'm doing here translate, scale, and reflection. And of course, these are the same matrices as before, so not surprisingly, it's the same result as we have done before. That's the x and y value, the pixel values. But as we said before, the z coordinate was still around. We were still set of 2. And to the z value, you also have access to, there's a specific depth buffer which you can access in the fragment shader. So what happens with the z buffer is very simple. The z buffer, the set from -1 to +1 will get mapped into a range from 0 to 1. So 0 will be closest to the camera and 1 will be furthest away. And you can change this. However, you cannot go beyond 0 to 1. You can make it smaller, but you cannot make it bigger. So the depth range, there's a GL depth range command where you can set near and far. Now this will result into the depth buffer being filled, the values in the depth buffer. The depth buffer traditionally is an integer buffer, starting with 16 bits and often too small. But that's restriction is long gone, and you can have larger buffers, and you can even have floating point depth values. Nevertheless, there's still effects where two scene depths map to the same level, and that can be tricky. Obviously, not when you do floating point or very unlikely if you do floating point, but with any integer buffer, that's the case. Okay, so that's it. Now we went all the way from the scene coordinates through the perspective projection of the camera, then from the orthographic volume into the canonical viewing volume, and then from the canonical viewing volume into the screen, so the buffer, and also the depth buffer.